Or you can also have real J. Generically, you have a real J, that's a non-normalizable vertex operator whose wave function blows up as you go down the cigar. But it turns out that, well, go back to this case for a second. In this case, what it describes is a scattering wave of the string that goes in and scatters back out. Some scattering phase, which one can compute. For real J, you can view this as an analytic continuation of that, but it's not well defined as a vertex operator because it just blows up exponentially. But there are some special values of J where, so a priori you expect these vertex operators to be something that's exponentially falling off and exponentially growing. But for some special discrete value of J, the two branches decouple, and you can keep the vertex operator that's exponentially dying off at infinity, so that corresponds to some normalizable vertex operator. Those occurs at some discrete values of J. So at J equals some special discrete value, which is of the form m 0 minus 1, m 0 minus 2, the constraint to be bigger than minus 1/2, also less than k minus 1 over 2, where m0 is some constraints. They're the minimum value between m and m bar when m and m bar are both bigger than 1/2 or both less than minus 1/2. So these results were obtained by studying very carefully the reflection coefficients, which can be calculated exactly and really expressed in terms of ratio gamma functions, and you'll arrive at this spectrum. Well, usually one might want to say that these details are not important, but it's actually very important for me. So, but unfortunately, I won't have time to explain all of that, and I'm running out of time now. So let me just say what I'm going to do with this. Once one identifies, so the first thing one can do is to identify the vertex operator that corresponds to the massless gluons, or the scalars, on the Coulomb branch of that 60-gauge theory. And there are many other things which you can also study, but these are the most basic objects. And so one will have to calculate their scattering amplitudes through, let's say, starting at tree level, through this diagram like this. So you have so if you look at the bosonic modes, you have some NS, which, as I mentioned, give rise to the scalars, and Raman fields that give rise to the vector bosons in this case, in 6th dimension. You can calculate their scattering amplitudes. In order to do that, you have to know the 4-point function of these normalized vertex operators. And that's a non-trivial CFT problem, which previously was not actually solved. And we were only able to calculate these things numerically through the explicit conformal block decomposition of, well, first of all, one would relate a certain class of covariant functions called one-number conserving correlators in the coset theory can be lifted to covariant functions in the SL2 WZL model. To calculate covariant functions in the SL2 WZL model, or more precisely, it's actually called the H3 plus model for some subtle reason. This was understood through the work of Rebold and Teschner. It can be related to covariant functions in Liouville theory. So we'll be able to recast the computation into a computation of 4-point function in Liouville theory, which, as you might know, generally does not have explicit expression, closed form expression, but you can, all the 3-point function Liouville theories are known, so you can write a conformal block decomposition for this 4-point function, which then has to be calculated numerically. So we will actually need to use some Lochkov's recursion relation to determine these conformal blocks and calculate numerically what these 4-point functions are, integrate over the moduli of this vertex operator and get the string amplitude, which is what we did in our paper. And that will be compared to perturbative expansion of 60 Yang-Mills theory. And a particularly non-trivial piece of that is the two-loop amplitudes. I'll explain why next lecture. Why is the two-loop comparison that is the first interesting and non-trivial comparison to double-scale string theory. And this is where we use the method of the unitarity cut, and we're able to obtain the scattering amplitude of these massless gluons on the Coulomb branch of 60-gauge theory, which will agree miraculously with the numerical result from the double-scale string theory. Next time.
last check you are commenting on, basically you are relating the conformal block in the Liouville theory with basically, is it the correlation function in the Yamio?
The relation is not between the coordinate function in Liouville theory and scattering function in Yamio's theory. The relation is between the integrated coordinate function in Liouville theory, where I have to integrate over the position of the vertex operator. Okay. So this is a usual string computation, like in the Veneziano amplitude, where you fix 3 vertex operators, integrate the 4th vertex operator. So you're integrating the cross ratio of the 4-point function.
Okay.
And after doing that integral, you get some function of the external momenta, right. Which is the amplitude. And that amplitude is the thing that's compared to the gauge theory.
What quantity is the scattering amplitude in gauge theory?
The scattering amplitude in the gauge theory of the vertex operators, of the gluon modes or the scalars that correspond to these vertex operators. So you have to choose the right vertex operators and identify precisely what they are, and you will, which we did identify in this coset theory, and that's supposed to be compared to the scattering amplitude. Now, you can ask scattering amplitude at what loop order and all that. And the answer to that question is that here, there's alpha prime expansion. Okay. So here, there's a string coupling expansion, and there's alpha prime expansion. Right. The alpha prime expansion is going to match on with the loop expansion in the gauge theory side, in principle. That's a direct dictionary. Whereas the string loop expansion, as you remember, it was expansion 1 over mw. Right. So the picture is that on the Coulomb branch, I'm doing the expansion here from string point of view. It's a large radius expansion on the Coulomb branch. Right. So on the gauge theory side, if the theory had been UV finite, you compute your amplitude, you expand it in 1 over W boson max. You get some series expansion. Term by term in that series expansion is supposed to be matched to tree level, 1 loop, 2 loop string theory answer. Right. But if you just do a tree level string theory computation and do the alpha prime expansion, you will, in principle, you should obtain, if the duality works, you should obtain all loop answer in gauge theory expanded to first order in 1 over mw squared. So the non-trivial test, so the 1 loop test was previously has been studied. The non-trivial test is a 2 loop, and that's what we did.
I'm just curious if there's something like in the same spirit like AGT. There's no your.
No, I think it's very different.
You have a super Liouville theory.
Yeah, but the relation is actually very intricate. I would say here, when I mentioned Liouville, that was for the purpose of computing these correlators. It's really
right. There's no trivial map between the
the non-trivial the map of Ribot and Teschner actually maps the endpoint function in the SL2 of the model to 2n minus 2-point function Liouville theory integrated. So you'll map the 4-point function to a 6-point function Liouville theory integrated. So you might think that 6-point function Liouville theory is pretty horrible, and it is. But luckily for us, we only need to look at certain limits of that 6-point function, which actually again reduces to a 4-point function Liouville theory. But there's a non-trivial step there, which I haven't.
And this is only for low rank, like SU2 gauge group, right?
No, this is for any gauge group, so SUK. So when I say numerics, we did this explicit for K goes 2, 3, 4, and 5, and so far I'm just talking about SU2 mod U1. There's another SU2 mod U1. SU2 mod U1 is the n equals 2 million model. So these are in principle exactly solvable, but in practice, it can still get pretty complicated. So at K equals 5, the 3-state Potts model was involved, and we actually need some results of the 3-point function in the 3-state Potts model, and they magically produce answers that agree with the K equals SU5 gauge theory on the Coulomb branch.
But do you expect if we are further compactify the 6D theory on some, well, down to some 4D, and in some kind of localization to verify this, to match on to your some quantity I can calculate in the result of the 4D gauge theory?
That's completely unclear. It's not obvious that the compactified theory would know anything about scattering amplitude in the uncompactified theory. Right. You can perhaps draw the analogy with n equals 4 super-Mills. So let's say you compactify n equals 4 super-Mills on the Riemann surface to 2 dimension, where you get sigma model on Hitchin modulated space. How would that capture a scattering amplitude of n equals 4 Mills? It's not so clear.
Okay, so let's thank Xi for his nice lecture.